Resume recording. Okay, well, it happens. All right, so you have your lecture slides. You can download them. You can print them out. You can bring them to class. You can have them up on your computer, however you want to do it. But all my slides are there. I actually had to sit and take notes with a mask on, and it's hard. It is. So I wanted to make sure you had all the slides. I'm going to do some practice problems in class and on the videos, and this is the link to that file. And then all the pre-recorded lecture videos are here, and you'll see there's a playlist, and we have the whole chapter done already. And then once I have the Zoom sessions recorded, I'll post them here as well. Okay? All right. Now we can actually get to the nitty-gritty. All right. We can jump right in. That didn't take long at all. All right. Any questions so far before we actually start on content material? Something non-content related. And I should have my chat open, but it keeps going away on me. Okay. Watch. No. Before Thursday, you're going to watch 4, 5, and 6 before Thursday, because we're going to do 1, 2, 3, then you'll watch 4, 5, 6. Alicia, does that make sense? Okay, good. All right. So can I get a volunteer, a couple of volunteers from the front? Those of y'all who are on computers who can have the chat up kind of on the side, just to like signal me and say somebody's on the chat, because sometimes I get to talking, and y'all feel free to interrupt me at any point. You have a question, please stop me. Don't just sit there with a question. Please stop me. Okay? All right. So I'm going to kind of leave it down there so that I'm not blocking anything. Okay. So we have 6 sections in this first chapter. It's quite a bit of material all at once, but we have 12 to get through. So we're going to hit the ground running. So classifying matter is our very first goal. All matter is classified into one of 2 things, either pure substances or mixtures. And I'm trying to find a good place for this so that we don't block anything. But all of these slides are posted to Moodle, so you don't have to write down every single thing. But if you don't have it today, that's okay. So when we talk about matter, matter is anything that takes up space and weighs something. So guess what? You matter, right? Do you take up space? Yes. Do you weigh something? Yes. So in the scientific community, we don't say that something takes up space, we say it has volume. We don't say that it weighs something, we say it has mass. All right? Okay, so here's our diagram for matter. We have 2 major divisions. The green division is pure substances, the yellow are mixtures. So our pure substances, when you think of something that's pure, what does that make you think of in your mind? All one thing, all water, right? Do I have a pure substance in this fish tank? Do I have all water in the fish tank? No. I have some Coke and some Diet Coke in here. It is not a pure substance, right? We have a mixture there. So a pure substance has to be either something you find on the periodic table, an element, or it has to be a compound. And a compound is a combination of elements. So the example of water, on the chat, all right. Oh, which MyLab and Mastering? The cheaper one. If you have not purchased the MyLab and Mastering, that's a really good side note. If you have not purchased it, there's a modified mastering and a mastering. The modified mastering is cheaper. That's the one that you pick. If you only see 2 options now, it means that they've done away with the mastering, which is what should have happened before the semester started. So one of the cheapest option has just the homework access, and then I think it's like $94 is the homework and the ebook. Okay. Does that answer everybody's questions on that before I go on? Is there a link for a respondus? Not yet. when exams come, I'll tackle respondus, but I'm not there yet. Purchase, so you want an option with a book and you want an option with a homework, so you can either get a hard copy book and the homework, or you can get the ebook and the homework, but you need both. So the $94 option, if you want the ebook, is fine. Okay. All right, so pure substances. We're thinking all the same thing, right? So elements on the periodic table, or elements that have been combined together to make one substance. So an example of a pure substance can be pure water, all water. So if I had a sample of pure water, every single particle inside of that substance is made up of H2O, every single particle. So it could be either an element that we find straight on the periodic table, or it can be a compound. Now, there's a caveat with those elements, right? You all know what the periodic table looks like. You can find an element, chlorine, fluorine, hydrogen, oxygen, right? All that kind of stuff. But sometimes you're going to see something as like H2. Have you ever seen H2 before? Yeah, is that an element? It is, no, it's all one element. H2 is all H. So technically we classify that as an element because it is all one element. Even though they are chemically bound together, they are still all one element. So an example on this one, H2, is an element, okay? Other examples of pure substances, NaCl, salt. Every particle of salt that you have is made up of sodium and chlorine. Table sugar is another one, aspirin. They all have a chemical formula that has to be exactly the same. Mixtures, on the other hand, this is an example of a mixture. There are two kinds of mixtures, homogeneous and heterogeneous. When you think heterogeneous, I want you to think different. When you think homogeneous, I want you to think the same. So we said this is a mixture. Homogeneous or heterogeneous? Is it all the same in here? No. So it must be heterogeneous, okay? Now, what if I took all these Cokes out, which I will eventually have to do, and instead of putting Cokes in, I put salt, and I gave it a good stir. What happens to salt when we put it in water? It dissolves. It all looks the same. So that would be a homogeneous mixture. So no matter how much I stir this, am I ever going to get these Coke cans to dissolve in the water? No. So that's a heterogeneous mixture. Didn't know how helpful this little demo here was going to be today, but it was awesome. All right, so we said two types of matter, pure substance and mixture. The pure substances are either elements or they're compounds. Elements are one thing on the periodic table. Compounds are a combination of things found on the periodic table. Then you have mixtures. Mixtures are either homogeneous or heterogeneous. Homogeneous meaning the same, heterogeneous meaning different. All right, so we said a pure substance has to be made up of the same thing. We can represent it with one chemical symbol, right? So if you're going to do that with one chemical symbol, what does that symbol represent? If I say I have a brick of gold, that means that my brick of gold all has what inside of it? One kind of atom. Atom is the simplest form of matter, right? So you have all gold atoms inside of your brick of gold. That's what makes it a pure substance. That's why every single element is a pure substance. When we talk about compounds, you're going to have a pure substance, but it's going to be made out of those elements, and they are chemically joined together. So sometimes it's covalent bonds, sometimes it's ionic bonds. It's all different ways that they are chemically linked together, but you're going to have that same formula. So no matter if you go and sit at my dinner table or anybody else's dinner table and they put salt on their food, they're putting NaCl and I'm putting NaCl. It's the same chemical formula. So now, we said that's pure substances. Mixtures, on the other hand, are a combination of two or more substances. So I said we had NaCl, we know that that's a pure substance, and we have H2O, that's a pure substance. When we put them together, do we have a new chemical formula? No, no. The water exists and the salt exists, and the salt is being dissolved, but it's still salt, right? So you don't have a new chemical formula, so you're not making a chemical bond between the salt and the water, right? So that's a mixture. A mixture can be separated. If I had salt water, could I separate the salt from the water? Absolutely. All I have to do is heat it. The water will evaporate and the salt will condense down at the bottom. So we can definitely separate it. And we said a homogeneous mixture, scientifically, we're going to say one whose composition is uniform throughout the entire mixture. A heterogeneous one is whose composition is not uniform. So here's my, look, I can pick out the Coke, right? That's a heterogeneous mixture. So I'm just showing you some other examples. Here's copper. You know, they use copper a lot of times in pipes and things like that, but it's all copper in there. The compound we've been talking about already was water, so that's a pure substance. We go over to mixtures. Here's a mixture you probably hadn't thought about before, an alloy. An alloy is a mixture of atoms inside of a metal. So brass, for an example, is a combination of both copper and zinc, and you can actually separate them if you heat them. It's a little convoluted, but you can separate them. And then here's an example of a heterogeneous mixture where we have copper, solid copper at the bottom of the cup, and then water on top. If you were to look at the molecular level, you could see the water up here and the copper down here. So you could be able to pull them out. All right, so section 2. We talked about these elements. Where are these elements? They're on the periodic table, right? These are all the elements that are found on Earth. There are some that we keep adding. How is it that we keep adding elements to the periodic table? That's kind of weird. They're super unstable. They're made in the lab, and they're very, very, very unstable. So that's why you'll see new ones. It's not that we've discovered something new in the Earth. It's that we've actually created something new in the lab, and it just doesn't last very long. So we've never seen it before it was created. All right, so inside that periodic table, you got little blocks, and you have letters inside the blocks, and each letter has some numbers and some symbols. And in the next chapter, we're going to talk about what all those are and what they mean. But the symbol themselves represent the names of the elements. Some of them are super, they make a lot of sense, like carbon. Carbon's letter is a C. Really easy, right? Gold. AU, why is it AU? That's kind of crazy, right? It's because it was Latin. It was a Latin word for gold, and so that's how it was written on the periodic table. So there are some that are a little bit strange, but I'll help you find them, don't worry. You're not gonna be all by yourself. So there are a few things when you're looking at the periodic table, you wanna know where things are. You have to be able to orient yourself. So you have to be able to find periods. You have to be able to find groups. Where are our periods? Down the side, we have periods 1 through 7. So a row is a period. A group is a column. So we have the noble gases right here. This is a group. We have a period here. This is period 6 going across, okay? So you need to be able to find anything on the periodic table. I gotta keep moving this around. So the vertical column is the group, and within groups, we have very common chemical behaviors. So if we go back real quick to our, if I could go back. Oh, I know I'm gonna click and it's gonna advance. There we go. So if we look here, if I said period 5, are the things in period 5 similar? Well, over here in the yellow, we have nonmetals. Over here in the blue, we have metals, and over here in the green, we have metalloids. Do you think metals and nonmetals behave similarly? No. They're very, very, very different. But if I take one group, everything in this one group is, guess what? The same kind of element, right? This is all non-metals. So things that have things in common tend to be in the same group, not the same period. So be careful about that. There are two different designations for groups. There's the IUPAC way, and there's the non-IUPAC way. IUPAC is the International Union of Pure and Applied Chemistry. So you can number these groups. One, it's in the parentheses, see 1, 2, 3, and it all the way counts all the way up to 18. That's really easy, you don't get lost. But there is another way to name them, and your book uses both of them. So you could name this the main group elements have a letter A. So here's 1A, 2A. Now to get to 3A, I've got to jump all the way across here, and I've got 3A, and so on. And then my transition elements are labeled with a B. So be careful if you see a 3B that you go over here. And if you see a 3A, you go over here, okay? It's one thing I see a lot of people miss. So we know that horizontal row across is a period, and our periods go 1 through 7. The other interesting characteristic that you need to know on the periodic table is this staircase. You see how they outlined it in kind of bold? We're transitioning here from metals to non-metals. So all of these greens, these are metalloids, except aluminum. Aluminum is kind of special, okay? When we talk about chemistry, there are some elements that are super important for our bodies. There's a big 4, C-H-O-N, carbon, hydrogen, oxygen, and nitrogen. Some people say CHON, just as a little mnemonic thing to remember, right? They make up most biological materials. Have you heard people say we're carbon-based life forms? Heard that before? But I thought we were 70% water. We are. So if you took all the water out of us and you looked at the most common element, that would be carbon. So if you looked at our dry weight, kind of a weird thing to think about, but our dry weight, no water present whatsoever, what you would see is that we have about 1,000 times more carbon in us than is in the earth. So we're very, very carbon rich, very carbon rich. So carbon's our number 1, and then the other 3 are super important. So those aren't the only 4 that your body uses though. You have what are called macronutrients. Macronutrients, you need at least 100 milligrams per day. So sodium, magnesium, potassium, calcium, chlorine. A lot of times if you pick up a vitamin bottle, these are the things that'll be on the vitamin bottle, right? And then there are some micronutrients. You don't need a lot of them, but if you don't have it, you're gonna be in big trouble. Iodine, fluorine, iron, zinc. Let's talk about iron. Where do you find iron? Why is iron? What? I heard it. In your blood, it's in your blood. So the iron is in the hemoglobin, which is inside of your red blood cells, and that's what picks up the oxygen so that you can oxygenate your entire body. So if you don't have any iron, you're not going to be doing very well, right? That's anemia. So here are our important ones highlighted on the periodic table. The kind of yellowish ones are our big 4, and then we have our macro. And macro, y'all know, means relatively large. Right? Micro means small, macros, relatively large. Okay, so now that we've kind of talked about the elements by themselves, now we're going to start putting them together. When we look at a chemical formula like H2O, what is that telling us? There's lots of information just in the name. It's telling us 2 what? 2 hydrogens. What about oxygen? We only have 1. If you don't have a number written, it's assumed to be 1, right? And so when we write our formulas, you'll never see a 1 because it's just assumed that it's there. Same thing's true about sodium chloride. You're always going to write sodium chloride NaCl because it's a 1-to-1 relationship between those two atoms. Now, NaCl is ionic and water is covalent, so they're a little bit different, but we'll talk about those differences later on. But it tells, anytime we look at a chemical formula, it tells us the ratio of atoms present inside of that compound. So NaCl is a 1 to 1. How about oxygen to, how about hydrogen to oxygen in water? 2 to 1, right? So it just tells you a ratio. How can you change matter? Physical changes are easy. They're reversible, and a physical change is just a state change, right? You know your states: solids, liquids, gases, right? We're still doing really good on time. Feel good. All right, so our state of matter can change. Think about water. Water is the easiest one because you have experienced water in all 3 states of matter. You've experienced it as a solid, as ice, then as a liquid, which we just call water, and then as steam. So when you look at the atoms in ice, what you're gonna see is that they don't move. Well, I say they don't move. They don't rearrange. They vibrate a little bit, just a little bit, but they don't move a lot. And they're in a particular orientation, and they don't change that orientation. So that if you crack your ice tray, right, and you dump it out into your tray of ice there, and you close the freezer door, your ice keeps that shape. So it's a solid because it's not going to change shape, it's not going to change volume. What happens when you then put that ice in your glass of water? It's going to melt, right? Now you have a liquid. Now you can take the shape of the container, but your volume's still the same. If you go on to steam, you heat it. What happens to those particles? What's happening to the speed as we go from ice to liquid to steam? It increases. We're moving faster and faster. Those ice particles were barely able to move. They're just kind of slightly vibrating. In liquid, they slide past one another, moving around. And in steam, they are whizzing around. They are far from each other. They've expanded as much as they can. They are moving super fast. But it's all just a physical change, because if you look at a molecule of steam, a molecule of water, and a molecule of ice, tell me, what is the ratio of hydrogen to oxygen? 2 to 1. Your chemical composition didn't change. Your chemical formula is the same, even though you change states of matter. So that's a physical change. If I take a sheet of paper and I ripped it, do I still have a sheet of paper? That's physical. What happens if I take a sheet of paper and I burn it? Can I get my paper back? No, you're done with it, right? That's a chemical change. You can't go back, right? So a chemical change results in a change in the chemical identity. I went from a sheet of paper to ash. Those are 2 different things. So what's going to be easier, a physical change or a chemical change? A physical change, we had to get fire out to convert paper into something different. So physical changes are typically require less energy to do. All right, so how do we represent how things change? We use chemical formulas. I know you've seen chemical formulas before. On the left-hand side of any chemical formula, we have reactants. And on the right-hand side, we have products. This little arrow in the middle means they react to form. So we go from reactants to products. And what you're gonna see are little letters behind each of the formulas. And they're telling you what state of matter. So S is for solid, L is for liquid, G is for gas. And I don't know if you've ever seen this before, but AQ is for aqueous. So if I took NaCl and I put it in water, did the NaCl become a liquid? No. I would have to heat NaCl up a lot to turn it into a liquid. But I didn't do that. All I did was dissolve it. So if you have salt inside of water, you would write NaCl in parentheses AQ. And that's what aqueous means, that you've dissolved it in water. You have to balance chemical equations. You cannot create matter. You cannot destroy matter. We can't do it. That'd be cool, but we can't. So you have to have the same number of atoms in the reactant as you do in the product. So you pick one element, pick carbon. However many carbons are in the reactant, how many carbon atoms, you have to have exactly that same number of carbon atoms inside of the product. Matter only changes form, not amount, right? We can shuffle the carbons around, we can put different bonds on them, but we can't create carbon atoms and we can't destroy carbon atoms. So in order to balance chemical equations, we use coefficients. Let me move this over. So if here's our chemical equation, carbon plus oxygen yields carbon dioxide, okay? How many atoms of carbon on this side? 1. How many on this side? 1. Okay, that's good. Now I'm going to check my other element. My other element is oxygen. How many do I have here? 2. How many do I have here? 2. Are we balanced? Check. Yes. Are they always going to be balanced? No, you're going to have to do that. So I'm going to show you. So what do you do? What do you do when you're balancing an equation? First of all, you check. That's what we just did. If you check, it's balanced, you can move on. If it's not, here's a big tip. A lot of people say, I don't know where to start when I'm balancing a chemical equation. This is where you start. Balance elements that appear only once on a side first. Sometimes you're going to have chemical equations where you have oxygen in 2 reactants, but oxygen only in 1 product. Then that's a good place to start, because you can just change 1 coefficient to change the total number of oxygen on one side of an equation. And I'll show you how to do that. And once you think you've got it right, go back and check, because sometimes you make mistakes. So always, always, always at the end, check at the end to make sure that your equation is balanced. Okay, so I'll show you how to do that right now. All right, so I'm going to try one more piece of technology. Let's see if that works. Maybe. Okay. Ooh, yay. All right, ooh, I moved it over. So this is the in-class problems that I was telling you about, right? Does everybody have that? You were able to find it, access it, right? I stole these questions from the textbook. So what I did was I just pulled all of their questions and put them all together in one place for you. So you can kind of have a place to go back to and you're like, oh, I know I solved something like this before. Well, this helps you kind of keep track of it. So I'm trying to help you stay organized. So when I made these videos, what I do is I lecture a little bit and I show you some problems. Lecture a little bit, show you some problems. So you'll see that when you go in and watch the videos. But let's talk about classifying. Let's go through a couple of problems from all the lectures we talked about today. Let's classify things as pure substances or mixtures. Iron, where would we find iron? Periodic table, right? Let me put my chat back up, if I can. Oh no, I don't know how to get my chat back. Well, I'll have to check the chat later, and then I'll figure that out. I'll figure out how to do it. All right, gelato. Anybody had gelato before? It's delicious. Yes, I see a few head nodding. It is Italian ice cream. So if you know anything about ice cream, you gotta use some milk, you gotta use some sugar, you gotta put some flavor in there. Maybe you like, I like pumpkin flavored. Strange, but very delicious. So you're putting all this stuff in. Anytime you're making something like a recipe, what are you making? A mixture, right? Spring water, Where do you get spring water? Is it pure water? No, it comes from a spring outside. You got dirt, you got contaminants, you got all kind of stuff going on in there. So it's not pure water. Unless it says pure water, it's not pure water. How about well water? Pure substance or mixture? Holler it out. What's that? Mixture. Because as I said, if it doesn't say pure water, it's not pure. Ocean water. Absolutely a mixture. You even got some fish in there, right? Cement. Mixture, good. How about a tropical smoothie? Mixture. Right? Even though it's all blended up, there are bits and pieces of different things inside of there. Right? Okay. Now we have some mixtures. We want to know if they're homogeneous or heterogeneous and why. A bowl of vegetable soup. God, this is making me hungry. Bowl of vegetable soup. That's, what if somebody made you a bowl of vegetable soup and you're like, oh, I really don't like mushrooms. Why do they have to put mushrooms in there? Could you pick out the mushrooms? Absolutely, right? So you got all kinds of different things. You could pick out individual things. That must be heterogeneous. Mouthwash. Homogeneous. If you go to take a swig out of your mouthwash and you got things floating inside of it, you got problems. You should probably get a new bottle of mouthwash. Okay, so that all looks the same. How about an unopened can of cola, of soda? Now you can't see through the can. We need a clear bottle, right? It's all the same. So it must be homogeneous. A dinner salad. Why did they put olives on my salad, right? Just pick them off. That's heterogeneous. Ooh. Okay. How about a bottle of sports drink? Homogeneous. Blueberry pancake. Heterogeneous. You can pick out those blueberries. Gasoline. Can you turn off your output? Okay, good. So gasoline, what did we say? Homogeneous. We can't tell any difference. A box of Raisin Bran. That would be heterogeneous. I can pick out those raisins if I don't want them. All right. So let's come down. We're going to talk about the periodic table. All right. Classify as an element or a compound and explain your classification. Aluminum. Where do we find aluminum? We mentioned aluminum today. If I came up here, where's aluminum? Right here. So is aluminum a element or compound? Element, because we found it on the periodic table. Sodium hypochlorite. Now, do you have to be able to write the formula based on the name? Not yet. Not yet. But just hearing sodium you've got to know is an element. Hypochlorite, okay, that's more than just sodium. That's all you have to know there. So that has to be a compound. It's more than one element. It's more than just sodium. Hydrogen, H2. That's one element, right? Potassium chloride. Potassium and chlorine. We have two elements. What must it be? Compound. Okay, let's try a few more. Fe. That's an element, that's iron. Ooh, I'm still on a highlighter. Element. CaCl2. Compound, Si. Element. Ki. How did you know it's a compound? It's two letters. The second one would be lowercase if it were the same element, just like in A and C. Good job. Okay. I did this one on the video, so if you want to see that, go back. We'll do this one. Use the periodic table to supply the missing information in the chart. Sodium. Here's one you actually have to go and look up. Anybody know offhand? Na. Okay, so if I go and I look that up, and I go and find Na, I really need to get rid of this so that you can see things, right? Where's Na? Right here. So what are we looking for? We're going to want to know the period, and we're going to want to know the group. So you find the intersection between the two. So we're in group what? 1A, and we're in period 3. So we are in group 1A, and we are in period 3. What's another way to write that group? Just a simple one. Is it a metal or a non-metal? How did you know it was metal? It's blue. Metal. Okay, now we're going to go the opposite way. We're given the group and the period. We have group 2A, period 4. Okay, so let me erase this. Group 2A and period 4. So just draw your little arrows. What do we got? Calcium. Ca. Metal or non-metal? Was it blue? Metal. Okay, P, anybody know what P is for? Potassium. So let's go and find P. We're going to find P, and we're going to say what group is it in? 5A or 15. 5A or 15, and in period 3. Okay, so group 5A or 15 in period 3, metal or non-metal? Non-metal. Last one, group 5A, period 2. See if I can get rid of some of this. What did I say? Phosphorus, oh, I'm sorry. Phosphorus. Oh, thank you. Okay, 5A and 2. 5A and 2. So we need to find our junction. What do we got? Nitrogen. And what color? Yellow. Okay, nitrogen in, and the rest is filled out for us. So now we're going to look at a couple of compounds. This one's really, really, really easy. All you're doing is identifying the number of atoms inside of any given compound. So if you have LiCO3, how many lithiums do you have? 1. Carbons? 1. Oxygen? 3. Okay. H2O2. That subscript down at the bottom tells us how many atoms. How many hydrogen? 2. Oxygen? 2. C8H8O3. How many carbons? Hydrogens? 8. Oxygen? 3. All right, let's do another one. Let's do MgSO4. How many magnesium? Sulfur? 1. Oxygen? How many? 4. Okay. NaHCO3. Sodium? Hydrogen? Carbon? Oxygen? 3. So, you good on that one? All right. So, let's move on because I want to get to balancing. How much time do we have? About 10 minutes. Okay, I want to give y'all 5 minutes, 5 extra minutes to go out, just so that you don't have to get too close to everybody else. So let's go to balancing equations because I really want to make sure you have these. So look at 1.13. We're going to balance the reactions by adding coefficients in the blanks, right? In this case only, we're going to write a 1 when we need to write a 1. So if you look at A, the 2 gray atoms, how many do you have of that particular atom on the left-hand side of the equation? 2, they're only in that one substance. So what you would normally write is you'd put the element, and I just put an X just for fun, and I put a subscript 2, okay? The next one, is it the same element? No, it's red. That's how they kind of signify either a size difference or a color difference. So how many atoms do we have of that one? 2. Now look in the product. We have 1 of each in a single compound. So that would be like saying X2 plus Y2 yields XY. Is that balanced the way it was given? No, it's not. So we need to balance it. We have 2 of each on one side and only 1 of each on the other side. So what do? We need to add a coefficient in order to increase the number on the product side. I want 2 on both sides, so I'm going to put a coefficient of 2. Okay? Look at the next one. The next one, you're starting with the same reactants, but you have a different product. What's different? In that product, you have 2 of the gray atoms, right? So if I said that's X2 plus Y2, now I'm saying it's going to produce X2, Y1. Well, that's not going to work, right? We need to balance that. So if I have to change my Y's, I change that by putting, I have 2 on this side. I'm sorry. Yeah, no. I have 1 on this side. Here's my 1Y right there. I only have 1. So if I put a 2 here, what happens to my number of gray atoms? I went from having, let's see, let me write here. We started, right? With X, we have 2. Y, we have 2. And in our products, we have X is 2, Y is 1. So if I multiply this whole thing by 2, by that coefficient, what do I get now? I get 4 and 2. Am I balanced? No, what do I have to do? My X, I need to increase the number of X. So what do I do to that? To make it 4. Multiply by 2. So how do I multiply by 2? I put that coefficient, right? Because if you have 2x2, how many atoms do we have total? That's 4 atoms of X. Okay? It's going to be practice on balancing equations. If you struggle with balancing equations, you need to do practice. Okay? Which time we got? 1:14. Okay, I'm going to stop there. And y'all remind me, and we'll do a few balancing right at the beginning of class tomorrow, Thursday. But that gets us through section 3. If you want to go back in the video, I solved some of the problems on the video. If you just want to go back and catch up on a few things, you can. So I'm going to say, I don't know. We're supposed to dismiss y'all in like rows. So let's do the outer rows first. Y'all go ahead and go. So like the outer 2 rows on either side, y'all go in the middle. Let's wait until they kind of file out and then y'all go. Either way, front or back. And if you have any questions, you can come let me know. Good luck. If you struggle, please come see me. Please keep those masks covering your noses and mouths at all times. Y'all have a great rest of your day. I'm gonna turn the microphone off. Hold on. Okay, go. You can. You're supposed to be able to. I have never done it before. That's a really good question. Can you send me one in email? Okay. Okay. No, that's good. And then I'll see if you email me and I can email y'all. It's supposed to be. I have not used the clickers before, so this is new for me. But I will find out and I'll go back to that. That's what the spreadsheet's for. Perfect. Okay, y'all go ahead. Everybody in the middle, go ahead.
Regarding the textbook, can we use the fourth,
The third edition?
the one with the coconuts on it?
You can use it, so the chapters are all in the same order. They have different problems, but I'm going to give you the problems. And some of the sections are out of order, but as long as you're okay with that, it's fine.
So I can buy the one without the e-tabs?
Yeah, that's fine.
Okay.
Yeah.
Thank you.
A lot of times, that's how they designate it in the textbook, by color. You tell me, and I'm not going to do that. Okay, I got you. I will not do that. I promise. Thank you for telling me. Who's next? Try shutting your phone off completely and leave it off for like 2 minutes. Turn it back on and try again. And then if it doesn't work, send me an email. So put your app, it won't let me sign in. So you've got the refab. But it's the app on your phone. So turn your phone off completely, leave it off for like 2 minutes, and then turn it back on. Sometimes it's connection. If it doesn't work, let me know.
Is that like an iPhone?
Yep.
Like your course would turn off, turn it off, turn it back on?
Yeah, like some people have been having glitches, and that's kind of seemed to work. So try that.
I know I'm ahead of time, but are we at any point gonna have to memorize the periodic table? I've taken this class before, so.
You don't have to not. I'm gonna give you the periodic table, but you will have to know. Like if I tell you in a chemical reaction, magnesium reacts. If you have to be able to find magnesium on the periodic table with this system.
Okay, yeah.
But I'm not going to give you the blank periodic table. Okay, I'm not. You just have to use it. Yeah. Yeah, no problem. Yeah, if you're just coming in, go ahead and wipe down your bench with the little, I want to say wet wipes. They're not wet wipes. Cleaning wipes. Okay, my Zoom people, I will see y'all. Wait, let me get out of this and see if anybody had a question. Now I can see the chat. I don't know why that works. Okay. Oh, somebody else got my phosphorus, not potassium. Okay. All right. Any questions? Anybody still on Zoom? Participants, just me. Nope. Okay, so I can stop. Don't share. End.